So, hello everyone, and welcome to my talk, CMake from Basics to Building. First, a little bit about me. My name is Petr Kmoch. I've been doing C++ professionally for over 15 years. I currently work at Alteryx, where I work in C++ with a little bit of C# mixed in, and while I was one of the team of 3 developers who migrated our build system there to full CMake. Before that, I worked for a long time for Ricardo Software, where I was doing C++ with some OpenGL and championed the migrating the build system there to CMake. And before that, I worked for a while for the Saarland University and C++ and doing some heavy development on tools interacting with the CMake build system there. So I guess you can see the pattern by now. I happen to become the CMake guy, so which is also why I am actually giving this talk. So what I want to do with this talk. CMake is rather widespread in the C++ ecosystem. It's not ubiquitous, of course, there are other such tools, but it is used rather commonly, which also means there is a lot of legacy CMake code out there in the wild, or code written by people who had mixed skill levels in it, who had mixed ability to maintain it, or mixed, were given just not enough resources to maintain it properly, or it was abandoned, and so on. So sometimes it is difficult to find what the right way to use CMake actually is, and it seems like it's fighting against you all the time. So, which is not helped by the fact that CMake is rather idiosyncratic in some aspects of its language and usage. So I want to hopefully give you some solid foundations for how CMake is supposed to work, how it's intended to work, especially how it has evolved in recent years, because a lot of the legacy code you find there is actually legacy from CMake perspective. CMake has good reference documentation. I would say very, very good. So if you need to find how to do something, you can go to the reference docs and find it there, usually well described. But you need to know what you want to look for in there and why you're looking for those particular things. And this is something I would like to focus on my talk. Start with the basics. There's a lot to say about CMake, much more than could fit in an hour. So I will just focus on the basics for now. The basic principles. What CMake actually is. CMake is a generator of build systems. It is not a build tool. It is not something that you use to build your project, but it is something that you use to create the build system for a given build tool and platform. On the input, you have the project definition in a file that has to be named cmakelist.txt. And on the output, you get a build system, be it a set of make files or a solution and VCXProj files, build.ninja, something else. CMake is a free and open source tool, and it's primarily developed by Kitware Incorporated. It was originally released in 2000 in conjunction with the IDK project. And a very important milestone in CMake's history is the year 2014, when CMake version 3.0 was released. And we can consider this the start of what is still called, I believe, modern CMake, or the modern approach to doing CMake. And there was a big paradigm shift in the transition from CMake 2.8 something to 3.0. This modern approach is what I will be describing, and I will make callbacks to the old, or like refer to the old things, like why they were, or what is different now. The current release is 4.1.1, and there are roughly 3 releases of CMake per year. I've included links to the website and documentation and to the discourse forum, where you can also find me sometimes lurking and answering questions. So what is the input? The input, the project definition, is the cmakelist.txt file. There is a very short example on the slide. The CMake language in which these files are written is a specific CMake thing. It is not using any well-known script, again, released in 2000. And the language is command-based, which is the first distinction from other things we are used to usually. I would say that C, C++, and these languages are much more expression-based, in that you can arbitrarily nest expressions, you can invoke functions with the results of other functions and things like that. And this is not what CMake allows you to do. In CMake, it is strictly a command and its invocation with string arguments. You can have variables in there, but you cannot nest command invocations, for example. But you can have variables which contain a string or a list of strings, and sometimes these get interpreted as integers if it makes sense, like an index into a list, but internally everything is string. And there is dynamic scoping. You can have functions that can call each other, you can define functions, call them recursively, and so on. And there is control flow, like you can see here, if else, stuff like that. I will not be describing the language more because this is about the projects, not about the language. So we have the input, and what gives us the output? If compilers have a front end and back end, CMake pretty much does as well. There is the CMake language, and then there is output, the generator in CMake terminology, which is a build system specific backend. So CMake has a generator for different versions of Visual Studio, for Makefiles, NMake, Ninja, Xcode, and the Greenhouse Multi IDE. And each of these generators is a separate backend, something you choose. When I'm running CMake for my project, I want you to generate this build system using this generator, and this will write the build system files. The generators have one important property, which is that each generator is either single config or multi-config. I will not say right now what this means, just put a pin in this for now. We'll come back to it later. And because I need to establish some more terminology for that. And previously, CMake also had some extra generators, which could generate editor or IDE files for things like code blocks or Sublime Text. But those have now been deprecated in favor of what is called the CMake file API, because it is a maintenance nightmare to always add new editors to CMake and keep track with what they do. So it is much easier for CMake to provide what it does now, a JSON description of the project if you ask for it, and then the IDEs or code editors can read that and present your project. So that's this. We have the input, we have the output. How do we get from one to the other? This is the CMake process flow, and this is very important, which is also why this slide looks so different from the other ones you saw and will see. There are distinct phases to what CMake does. When CMake is running, there is a configure step and a generate step. In the first phase, in the configure step, CMake is running. It is reading the CMake list, the txt files and files you include from there, executes the command in them, but does not really act on them in any way. It does not generate anything. Nothing is set in stone yet. It was just building a map of your project, the idea of all the settings you want in memory. This is what it does, and then eventually the last line of the last CMake list.txt file is processed. CMake is still running, it is still CMake, but now it switches over to the generate step. There is no more CMake language processing, everything is in memory now. It will do whatever transformations, propagation, settings, validation it finds necessary. It may tell you that you specified some source files that don't exist or things like that. And if all is well, then the generator takes over and starts writing the build system files. And it will also write its own cache for later reruns. But knowing that these two phases are distinct is very important, because there are things that only make sense in the configure step, and there are things that only make sense in the generate step. And if you remember that these phases are distinct, then it will help you understand maybe why something is not working the way you might want to, or whoever authored that CMake list wanted to. So please keep this in mind. And I will be using the color coding of blue for configure, green for generate, and brown for build. I hope it's visible on the projector, but it is used throughout the presentation to keep the concepts separate. And then when generation is over, all the solution files or make files, whatever, are written, CMake is done. It says, dear developer, here is your build system, have fun, I step away. And then you have the build system on disk, and you use your native build tool, be this devenv or opening Visual Studio or running Make or Ninja, whatever, to actually drive your build. You can drive the build with CMake -build, but that is just a very thin wrapper for launching the native build tool. CMake is not involved in the build itself, which is again something important to understand, that it is a tool for generating the build system, not for actually building. Okay, but where does the generator actually write the build system? Well, where you tell it to, but there are two important concepts here, and this is the source directory and the binary directory of your project. The source directory is the one where the main CMake list.txt file is located, and you can have other subdirectories there. This is where you will expect all your source files to appear, and this basically corresponds to a version control checkout. So this is the source tree. And then there is a binary directory into which the build system is generated, where the generator writes its output. By default, this is also where the build artifacts and the build intermediaries like object files end up, and CMake's internal helper files. You can set, there doesn't have to be any relationship between the source directory and the binary directory on disk. They can be on different disks for all CMake cares. You can ask CMake to generate into the same directory as the source, but please do not do that. It is discouraged, and it may even be deprecated now, I'm not sure. But it's never a good idea to do that, because then you lose a very important property of CMake, and that is that you can have a 1-to-n relationship between the source and the binary directories. You can generate as many binary directories from the same source directory as you want. And for each binary directory, it's a different CMake run, so you can choose a different generator, a different compiler, different set of settings, whatever. Here we have 3, one for building with Visual Studio, one for building debug with GCC, driven by Make, and one for building release with ICC, driven by Ninja. And it is still the same source checkout that you have. So, and if you ensure that none of your build actually writes into the source directory, then you're fine. You can have those 3. You can build each of them. They will pick up new changes from the source. And if something goes catastrophically wrong in one of them, you can just delete the binary directory, start over. Your source is perfectly intact. So again, keep this in mind and try to keep all the build-related stuff in the binary directory. And I've mentioned debug release, so now it's time to come back to the configuration. Configuration is the CMake term for debug, release, release with debug info, min-size release. Those are the 4 configurations supported in CMake by default. And you can, with a little bit of work, you can also define your custom ones, which is not something I will show here beyond the scope of this, but it is possible. And some things in CMake are configuration specific. Well, most things I would say, like build flags, include directories, what you link, what source files you use, where the outputs are located and how they are named. All of this can be specified per configuration. There are a few things that are shared across configurations that are simply attributes of the project itself, which is like which binaries are produced. So you cannot easily have a different number of libraries produced in different configurations, but you can put them elsewhere, you can name them differently and so on, that's not a problem. And source directories, again, shared for all the configurations. And now is the time to come back to what single config and multi-config generators actually mean. Some generators like makefiles, and there are various flavors of makefiles supported by CMake, and makefiles and Ninja are single config generators. You choose which configuration you want in your build system at CMake configure time. You define the variable CMake build type to debug or min-size rel or whatever. CMake will run the configure, generate step, and produce a binary directory for this particular configuration. So this is what here or here would happen. But there are also multi-config generators, such as Visual Studio Xcode, Greenhouse Multi, and recently an option to generate multiple configurations for Ninja was also added. So Ninja, there are 2 Ninja generators in CMake now, one for one single config, one multi-config. And in these, the configuration is selected at build time. That is, who uses Visual Studio knows this. There is this drop down where you can choose whether you're building debug or release or whatever. And CMake can generate such a Visual Studio solution, and it does. All the configurations are there together, which means that it is generated by just one CMake run. The one configure step, then one generate step. Of course, the generate step will write the sections of the project files for each configuration or the conditions as is native. But it is one shared CMake run, which has a very important consequence, and that is that you should never have CMake configure time logic that is based on configuration. You will find this in the wild, especially in projects that originated in Linux, where single config make files are common. You will have if CMake build type string equal debug or something. If you do that, you prevent your project from working right with multi-config generators, because they don't have a CMake build type at configure time. It is not known yet. It will be selected by the developer eventually when they build, and CMake is no longer in the picture. So please avoid this, or be aware that if you do this, you prevent multi-config generators, such as even the Ninja multi-config, which allows you to not have to run CMake multiple times and not have multiple bin directories. So this is something best avoided. And I will show you a way how you can do configuration-specific things without configure time logic later. With this, we've covered the basic principles, and it's time, I think, to turn into what you actually build your project out of. And the most important building blocks are targets and projects and directories. Oh my. So the basic building block of a CMake project is the target. Target in CMake terminology is a library, an executable, a custom build step, or something similar. Basically corresponds to a make target, which is also where the terminology comes from, or to a VCX proj. And it is the basic CMake entity, and as CMake is evolving post the 3.0, it is evolving more and more towards seeing targets as the primary building blocks of your project. So you will see later what else happens with targets and how they're important. I keep using the word project, and I mean it in the general sense, like your piece of software that you want to build, but it also has a well-defined meaning in the CMake world, and that is a self-contained build system or a part of it. And you could say it corresponds to a makefile or to a Visual Studio solution, which is also what gets generated from each project command in CMake. There is always one top-level project, and every top-level CMake file basically has to start with CMake minimum required to specify the version, and then project to give the name of the project. The first call to the project command also initializes CMake's knowledge of the compiler you're using and things like that. And then you're free to go. And then there are the directories. There is again the top-level source directory. And you can have subdirectories which also contain CMake list.txt files. You add them with the add subdirectory call. And each of those has a corresponding binary directory. And the source directories form a logical hierarchy. They inherit some stuff from their parent directory, can override some things and so on. But this does not have to correspond to the physical hierarchy on disk. This is a logical hierarchy for CMake purposes. As you can see here, we have some kind of my shell application, which is an executable, and then two subdirectories. One which is a true subdirectory on disk, the net thing, but one which we want to treat as a logical subcomponent, but it actually lives at the same level as our my shell. It just defines a library. Perhaps other projects are using this as their subcomponent as well. Perfectly fine. And again, the myshell/net adds some libraries and adds the subdirectory. Logically, it will be under it, but in reality, it is on the same level. CMake does not care. There is the logical hierarchy, and that is what matters. As I said, the basic building blocks are targets, and the most common ones are the targets for the binaries, executables, and libraries. You create these with the command add executable or add library. You give it a name. For libraries, you also specify a type, and then you list sources. The basic types of library are static and shared, and there are some other types available as well. We'll touch on some of them, and there are more in the docs. The name of the target, this is the logical name of the target for CMake's purposes. It has to be unique within the entire project. By default, it is also the name of the generated binary with potentially platform-specific prefixes and suffixes prepended like lib or so, DLL, whatever. But it does not have to be. If you want, there are ways how you can easily configure the output name of the binary to be something else. So do not restrict your logical names of the targets just by what you want the binary to be called. Because if you want three binaries in different directories, three libraries called the same output file, it is perfectly possible, but they have to have distinct the logical names. And the other thing you give into this command are sources, and what you should list there. You definitely have to list the compilable source files. This is the bare minimum. This is what CMake will know to generate into the build rule for the target. But there are other things you want to put there as well, other contents like header files, auxiliary things like documentation, examples, whatever. And that is because in the IDE generators, like Visual Studio Xcode, or in the projects that, or editors that take their information from the CMake file API, these things will appear as logical components of the target underneath it. The CMakeList.txt file, which defined the target, will appear there as well automatically. You can add your other CMake files there if they are included within it and things like that. So whatever you want to be logically part of your project and of your target and accessible as such to the developer is there. Like for example, in this library, we also specify the user help as Markdown. And for this version library, you have a C and a Fortran include, for example. Don't be afraid, CMake will not try to compile the Markdown as code or generate such rules. And if it gets confused somehow because you have an example CPP that you do not want compiled, there is a way to mark it as this is not really a source you should build. Okay. So we have the target. How do we set it up? How do we configure it with things like include directories and so on? There are commands target underscore something, which always take the name of the target you want to configure, a scope, and then the items which are added to the target setup. Again, for the scope, we'll come back to this in a moment. So for now, we can ignore this. And there are commands like target include directories, compile definitions, compile options, link options, sources. So as you can see, for example, here, you can add sources after you've defined the target. Yeah, this should probably have been network and not my shell. Okay, never mind. You can specify, of course, options for different targets, so it's not really an issue. And there is also a special one. There is also for linking libraries. Specify what you want to link into your target. But I've put this on a separate line because it does more than that. And for this, what more it does, I need to specify what CMake usage requirements are. This is, again, a very important feature of CMake, of modern CMake, to be precise. Each target actually has not one set of the settings like include directories and defines and whatever, but two, the private set and the interface set. The private set is the one you normally would think about. This is what you specify when you build your target, which include directories it needs, what flags defines you want, what you want to link into it, and so on. But then, if your target is a library, it probably also has some requirements on whoever consumes it. They will need some of your include directories which contain the public API. They may need some defines or special flags. They may need to link against something because you use it in your public headers. And CMake allows you to express this relationship with the interface settings. These do not apply to the target itself as it is built, but these apply to the consumers. And whoever links against your library will automatically get these usage requirements set up for their target. And how do you do that? This is what the scope is for. There are three possible values for the scope argument or parameter. That is private interface or public, which the private interface populate the corresponding settings, and the public populates both. This is a very important feature. This is basically one of the things that differentiates CMake 3.0 and onwards from the previous ones, where user requirements started being used and being used more and more. And it allows concentrating the knowledge there where it is. You, as the author of the library, know what your consumers will require. So you just tell them, you configure the library like that, and they don't have to care. And they don't have to change anything if later you decide you need one more include directory because you split your hierarchy in some way. They will simply reconfigure and pick up the changes. They don't have to modify their own CMake list if it's managed by a different team or anything. I have an example here to drive this home. We have a network library which has a public include directory nw/include, which means this is where the public API lives. And it is also, of course, needed for the library itself, so it's given as public. And then there are some private headers in these directories apparently. Our network library uses Boost SEO, but it uses it internally, does not use it in the public API, so nobody else needs to link against SEO. And we have some defines, something again public, something private. And then we have an executable which uses the library, and this is all we have to do to configure the executable correctly. it will get the include directories, it will get the definition of the API version just fine. And then let's say we want to extend our network library with JSON support and in the public API as well. So we define a library that will do the JSON thing for us. Again, this has some public include directory and a private one. And let's say it also has public compile options because it is using pointers to member in its public API and thus has to standardize their representation. These are the flags for MSVC that do so. And we use it in our network, we use it in the public API. So what we do, we just start linking against this library publicly, which means we use it internally when building, but we also export its usage requirements as a subset of our usage requirements. So again, the changes that need to happen to my shell are precisely 0. But on next reconfigure, my shell will start linking against my JSON and will pick up its include directory so that it can reach the headers network is including transitively. As I said, CMake is moving more and more towards using targets and usage requirements as basic building blocks for your projects. So sometimes you have a collection of settings you might want to use, but do not really have a binary that goes with them. And there is still a way to express this in CMake, and that is as an interface library. That is a library named interface. That is a special type. It does not correspond to a binary on disk. It does not have sources. It's not anything that gets built, but it still has usage requirements. And you can use this for several things. The prime example is a header-only library. If you're developing a header-only library in CMake, there is nothing to build, there is nothing to link, but you probably still want your consumers to get access to some include directories, maybe defines other things. So you can create an interface target for your header-only library, give it interface, include directories, whatever, and it will get picked up, and the consumer can just say link against that library. CMake knows that linking against an interface library just means bringing in the usage requirements, and that's it. Another example use case is if you want a common set of options or whatever settings that go together. For example, we may have this notion that some of our targets will want to use stricter standard conformance. So we can create an interface library called standard, and we give it a compile definition of CRT secure no warnings, give it some interface compile options like permissive and the two-member two-pointer flags, and then we have our myshell executable, and we link against this library, and this just means the executable will now get this set of options and compile definitions brought in. So this is if you're thinking in if you have some logical grouping of settings like working with Unicode, which needs to link to set a certain flag and defines or whatever, just create an interface library. It will be easier for others to use them and for you to change it as it evolves. It has a logical name now. And there's one final piece of a final building block for your projects, and that is external dependencies. You probably have third-party libraries that you want to use in your project. You may have pre-built them, you may have them installed manually or come from a package manager. Something, they are there on your disk and you want to use them. It is perfectly fine to just say target link libraries and give an absolute path to the library, to the SO, DLL, whatever, and not DLL, lib. You need the lib for linking. But CMake will pick this up just fine and include the rule to rebuild your code if the library on disk changes. But probably the third-party things also have some sort of usage requirements you would like to do. And so a better way than just listing them by absolute path is to create an so-called imported target. You can create a library with the name and the given type and import and the keyword imported. And this means that you're telling CMake, I have this library and I want to register it with your set of targets. I want you to treat it as a part of the build, as a part of the project, except it will not be built. It already exists at this place on the disk. So you have this add library imported, and you can put user requirements on those. Again, normally, of course, ideally you do not do this yourself. It will be done by whoever authored this library, and it should be part of the definition of the package from which it comes. Because third-party libraries normally come from some sort of package, even if it is just the single one. And there is a CMake command, find package, which you give it the name of the dependency and some other arguments. And its purpose is to locate and read a CMake file which contains the description of the package. So this will be looking for a file which will have all those add library imported calls in it and its setup properties. Such files can even contain CMake functions for use in your project and so on. And the find package command has two possible modes in which it can run. The modern one is config mode, when it is looking for something called a package config file, which is named name of the package config.cmake. And this file is the one that is supposed to do the add library imported and whatever. And this file is provided by the upstream package itself. A lot of packages do that. If you're creating a package for use by others, and you're using CMake for it, CMake can generate this file for you automatically. It will just take the usage requirements as they are defined for your targets and generate the add library imported calls into the file based on those. But even if you are developing a package and for whatever reason you're not using CMake, but you want to be nice to people who are using CMake and you want your package to play nice with the CMake ecosystem, then you can define a package config file inside your distribution. And if you distribute it as part of the package, then CMake will be able to pick it up, or at least even if it's not picked up automatically because it's installed in an unexpected location, then at least the consumers will be able to easily point CMake, this is where the package config file lives on my machine, and then CMake will pick it up and set up the package for use accordingly. And there is also, as I said, there's also the legacy, and that is module mode, which was the original one, which was that it's not looking for a package config file, but it's looking for a find module called find name of the package.cmake. It looks like almost the same except a different name, but the major distinction is that the find modules are provided by the consuming project or by CMake itself. Again, this was the original way how external dependencies were handled in CMake, and if you look into the CMake documentation on modules, CMake modules, you will find there is a lot of find modules for find libjpeg, libping, boost, whatever. Of course, this is the exactly same maintenance problem as the extra generators for editors, except much worse because there are many more third-party libraries than there are coding editors. So this again became unmaintainable, and you cannot keep track of all the ways third-party packages develop and new third-party packages that are popular are added and so on. So CMake added again the mechanism how the package itself can provide its its information to you. So if you are developing a package, whether you're using CMake or not, please consider providing a package config file in the expected place. It will make your project that much more loved by CMake people. So there is much more to be said about using external dependencies in CMake and how it can fetch them sometimes automatically, how it handles packaging itself, but again, this is beyond the scope of this talk, unfortunately. And we've covered the basic building blocks, and now there is time to say something more about settings and customization of your project. For this, we'll peek a little bit under the hood of what all those target something commands actually do, how they set up those projects, because the targets, how they configure them, because that is something you can use and you can use in other things as well. And many entities in CMake, primarily targets, but other things as well, directories, source files, the global scope, have properties, have a set of properties. It is basically just a name value mapping. It has a set of named things, and these have string or list values each. It may sound similar to variables, but it is something different. The variables can be expanded at configure time using the $ and braces syntax, but they have global or function local scope, whatever. Properties are attached to a given entity. A target has properties, a directory has properties. You can get these using the get property command. You can set these or append to them using the set property command. And what are the properties actually for? Targets, for example, have things like include directories, interface compile options, and so on. And this property is just a list of strings. And all the target commands, what they really do under the hood, they just append to these particular properties. And you can, if you really want to, you can manipulate them directly. It is better to leave it to the commands, but you can manipulate them directly. The thing is, targets have many more properties than just those corresponding to those commands. There's properties like output name, runtime output directory, and other things which you can use to, as I said, to configure the name of the binary, where it's located, and so on. So if you have a logical target and you want under a name and you want the binary to be produced with a different name, you will just do set property, my target, output name, my very whatever executable dot com, because that is what you're building, and it will work. There are properties for certain flags, for example, interprocedural optimization. A certain set of compilation, let's say, flags or features is supported natively by CMake, in that you don't have to know the flag for your particular compiler. You just set, if you want IPO in your target, you just set its interprocedural optimization property to true, and CMake will know to generate /LTCG if it's generating for the Visual Studio toolset, and to generate dash IPO, or I don't know exactly what the exact syntax is, but CMake does for the linker. So if your toolchain is supported by CMake, then some properties are some flags are abstracted into properties. You can set them like this. I've included again a link to the list of properties of on targets. It is huge. Remember, I said you can have per configuration flags and settings, but I haven't shown how yet. Let's say we have this goal. I'm using Visual Studio example as my default because that is my default environment, and also because it is a multi-config generator, but the principles are of course identical. Let's say we want to define iterator debug level to 1 in our debug configuration, and we want to use stack 4 megabytes in the release configuration. If we just did this, what is there on the slide, added it to the compile definitions and link options, then it would apply in all configurations. That is not what we want. As I said, sometimes in the wild you will see code like this, but please do not do that. This is precisely what will not work in the multi-config generator case, such as Visual Studio. So that's not the way to go. So what is the way to go? I will show it. It will be ugly, but don't worry. I will explain what it does. So then you will hopefully understand it, but it will remain ugly. And this is what it looks like. CMake actually has a thing called generator expressions, or genexes sometimes for short. And this is another feature that was pretty much added with CMake 3.0 and has been expanding ever since. And what these do, it is a string with the syntax $, left angle bracket, name of the expression, colon, comma separated arguments, and a right angle bracket. Do not confuse this with CMake variables, which are dereferenced using the $ and braces syntax. This is something else. And generator expressions allow you to embed evaluation into properties, and as the name suggests, they are a generate time construct. At configure time, when CMake is parsing this thing I just shown with the target compile definitions private, whatever. This is precisely the string. It sees the literal string, a dollar, left angle bracket, whatever. This is what it will store in the property, plain string. But come generate time, CMake is now, let's say we are now generating our VCX proj for the myshell thing. We're generating the debug section of the configuration, and CMake encounters this property in the compile definitions, this text in the property compile definitions. And it says, okay, this is a generator expression, and I have to expand it because I'm at generate time. I know all the information I could possibly know about what is happening, and I will be generating all the configurations eventually. And how the expansion actually works, the basic two generator expressions, the most important ones, are 1 and 0. That is the name of the GenX, and the GenX 1 expands to its argument, and the GenX 0 takes an argument but expands to nothing. And then there are many Boolean tests, such as asking whether we are currently generating one of the particular configurations, which expands to 1 or 0, based on whether that is the case or not. So how does this work? The generator has encountered this GenX. It has to expand it. The innermost one is this, asking whether the config is debug. Let's say we are generating the debug configuration in the VCX proj now. So yes, this is a 1. It is true, so it expands to 1. There are no spaces. This just shortened the string. So there is still a GenX. We need to expand it. The GenX is 1, which, as I said, expands to its argument. So that is what will remain in the property compile definitions after the expansion. Fine, that is what will get generated into the VCX proj file. Now we are coming to the link options property. It's asking whether the config is released. No, we are generating debug. So that is a 0 again. The GenX 0 expands to nothing, and that is what will get generated, or actually not get generated because there's nothing there, into the link options. So this is the mechanism how you can do logic based on configuration without having to do that logic at configure time. You're doing it at generate time when CMake already knows everything there is to it, and it can generate the things differently. As I said, at configure time, generated expressions are a plain string, and more important, they have to remain a single argument. If you introduce line breaks for readability, it will cause this thing to be split into multiple arguments, and then the generator may not recognize it as a GenX at the generate step. So what you want to do for complex generated expressions is to build them up with variables. For example, like this. Let's say we have a variable not debug set to this particular string. Then an isClang, again another GenX whether the compiler ID is clang. Then we can define a user reporter to a conjunction of those two. And then finally we say that our target will have an additional source file if we are not in the debug configuration and we are using clang, then please add a file called reporter-$config. The GenXs are not just for querying and disabling, enabling. You can also use their values, like for example here. And here, if you want to build this project with Clang, you need to provide 3 source files: reporter.release, reporter.minsize.rel, and reporter.rel with dev info. You don't need a debug one because the debug one will be removed by the not config debug thing. So you can do many things with generator expressions and configure different properties with them. You can also, there's also a command called file generate, which you give it a GenX and it will, or a string containing GenXs, and it will generate the file onto disk at generate time, but which can again potentially have per configuration output, which is useful for if you need some build steps that depend on things. I've used this, for example, for generating some information for building a Python extension based on my targets. And it is also useful for printful style debugging. If you're doing a difficult GenX and it's just not behaving right, then you can send it to file generate, at least see what CMake thinks it should generate there. As I mentioned, generated expressions are a modern addition to CMake. I mean, there were a pretty limited ones in CMake for a long time in the 2 point whatever time. And with 3.0, more generated expressions started being added for things like asking a target for its properties and using it in my properties, there is now list manipulation and so on. What genexes do is always expanding. But unfortunately, since they were not there from the start, they are not something that is magically supported everywhere in CMake simply because they are there. Internally, every property that supports genexes has to be hooked into the genex expanding mechanism inside CMake code. So if you want to use them in a particular context, a property, a command, something, first consult the reference docs to see whether generator expressions are supported there. The docs are pretty good at saying you can use generator expressions in this context, in this argument, but check before you do so that you're not surprised. And what other configuration options are there? There are other ways you can set up targets in CMake, but more or less these are those I will tell you to avoid. The first one to avoid, obviously, is the compile flags property. It sounds very similar to compile options, I think, but it is much older and it is deprecated now because unlike compile options, which is a real CMake list, where CMake knows that it is a list with certain elements and knows to treat them accordingly, this is a space-separated string. So, which, with all the quoting issues, if you need something quoted in there, you have to care for it yourself because CMake will otherwise just split it by spaces, and it also does not support generator expressions. So, while compile options does support it. So, if you see old code doing things with escaping spaces and using this property, know that this is a prime target for refactoring into compile options, which is much more powerful, much more robust. Then there is a link directories property on targets and the corresponding target link directories command, which basically corresponds to the dash capital L on the Linux linker, for example, which basically tells it where to look for libraries. And while this thing works, it is discouraged because it leads to rebuild issues, and I've seen rebuild issues caused by this and hunting down why something is misbehaving. Because if you link a library by specifying the directory and then by just giving the name of the library, and you know that the linker will find it there, you know this, fine. The CMake does not, so it cannot issue rules into the build system for rebuilding if that library on disk changes, because it cannot see the relationship between the name of the library and the file in that particular directory. So if you want to use a library on disk, ideally you will create an imported library for it or get it from a package config file. But if that is not an option, at least give an absolute path to target link libraries. It supports absolute paths, it will pick up the library just fine, and it will also generate the rebuild rules so that you get the correct relink if the library changes. And another way things can be done are commands like include directories at compile options, and especially include directories is something you will probably find in existing code a lot. And it is almost similar to target include directories in the spelling, but it is not target specific. It affects the properties of the directory in which it is called and not of a particular target. And when a target is created, its properties get inherited from the appropriate properties of the directory. So it is a way to set up include directories for all targets in this directory or compile options for all targets in this directory and so on. This can be useful in certain cases, so I'm not saying do not use this, but I'm saying that CMake is moving away from this approach. It is moving more and more towards expressing things with targets, expressing things with interface libraries. So even if you have a set of targets that you want a certain configuration, they are all in the same directory, it is still probably preferable to create an interface library that will encapsulate all these settings, give it a meaningful name, and then you can just link this into all the target. This is one extra entry in a target link libraries call, and it will make the meaning more obvious, especially if the directory has subdirectories, and then you're 3 levels deep, and somehow include directories from this top level directory still apply to you. It is easy to forget. It is better to be explicit. And finally, what you will also, I would say, often find projects messing with, which they should not, are variables like CMake CXX flags, CMake C flags debug, and whatever. There's a whole family of these for compilation flags and linker flags, and so on. And notice that these are variables. These aren't properties. These are the things you set with set, whatever, maybe append. So, and these variables get applied pretty much at the end of the setup of the target and so on. When it's generated, then these variables, the flags get applied to the target as well. But they are not intended for projects to use, even if projects quite often use them. These are intended for end developer customization. These are intended for whoever checks out your code and they want to build it, and maybe they have a special compiler that needs an extra option, or they're using a new version, or they want to try what happens when they mess with the options. You do not want them to edit the CMake list.txt. And these variables exist for them as tweaking mechanisms where they can add their own flags and it will get picked up. So, and if your project interacts with these variables, sets them somehow, you basically rob the end developer of this customization option. You have your properties to set up your targets, leave the variable to the end developer. What other end developer customization? How does this actually work in CMake? If you are developing a project that you want others to consume, be it a library, be it an executable, whatever, there are probably settings that are changeable, such as whether you want to build the documentation, whether you want to build the examples, where you want to install it. There may be whether you want the libraries to be shared or static, where your external dependencies are located in case they're in non-standard locations. CMake has a mechanism for allowing projects to expose things that the developer can customize, and these are so-called cache variables. They're similar to normal variables. The command to set them is the same. Set a variable to, come on. I'm sorry. The mouse point. Okay, the laser pointer stopped working in PowerPoint for a moment, sorry. So set the variable to a value, but then you give it a keyword cache with a type, a description, and potentially force, but force overrides what the user chose, so that is not what you want to do. And this command sets the value unless it has been set by the developer already. This basically sets a default. So if you have some things you want to have configurable in your project, set cache variables for them. These will be the defaults that your project offers, and CMake has several UIs. It has this Qt-based CMake GUI. It has a console CMake that is using, I believe, Ncurses, a console UI, and the end developer can use the CMake GUI or the CMake or whatever to see the cache variables that are offered by our project, and they can make changes there. You can see a screenshot here, and what the type in the setting the cache variable, what the type does is change how the variable is presented in the UI. For example, these were variables that were given a type of bool, so they're presented as checkboxes. And this deplist file is a file path, so it is presented as a file chooser button. And this tooltip you can see is the description. So you can actually define your variables so that end users can tweak them. Those variables are stored in the CMake cache, and they can be some of them can be advanced. You can see in the GUI there is an advanced tick box, and if you tick that, you will see also the advanced variables. And among the CMake variables, which I've collapsed here, if you tick advanced, you will also see the CMake CX6 flags, debug, and whatever. And this is where the user can play with them. It is possible in CMake to have a cache variable and a plain non-cache variable of the same name, in which case the plain variable hides the cache one. So if you set, and this is especially irksome for the developers, because if your project sets CMake CX6 flags to something, then this will simply hide the cache variable. The user will have it, the end developer will have it there, he can set it, but it will get ignored because it gets shadowed by whatever your project set. Sometimes, in some cases, this may be what you want for probably for your own settings. Sometimes you just need to override them for some reason based on other settings, but you should not do this for the built-in ones. And this is what an end developer's workflow is actually intended to look like, what CMake expects, how CMake expects CMake projects to be used. You configure, so if you have a plain checkout, empty binary directory, nothing happened yet, you run configure, and then you get the list of cache variables, because as CMake is processing the CMake list, it finds the set something cache. Yeah, okay, I will know how to present this. The developer looks at the cache variables. Are they good the way they're set? Maybe not. Maybe it didn't find a dependency I have installed in a weird location. So I will modify the variable boost root, whatever, to where I put it, and configure again. This time the new value will be used. Maybe it's found now, fine. I can keep iterating the configure step. Some UI, both the UIs, both the CMake GUI and CCMake allow you to do just the configure step. There's a separate button for configuring. If you're running CMake from the command line, it always does one configure, one generate. But in the UIs, you can just iterate configuring. And once you're satisfied with the setup, then you hit the generate button. The generator takes over, generates the build system, CMake terminates, and you are now happily developing and building. And this is all I could squeeze into the hour. So just a quick takeaway, what I think are the most important points from here. The first one, be aware of the distinct phases. There is a configure step when CMake is processing the CMake list files. There is a generate step when the CMake list files are no longer touched. Everything is in memory and it is being written to disk. And there is a build when CMake is no longer involved. It cannot do anything at that point. There are multi-config generators. So configure time conditions should not depend on generate time information. There are generator expressions for that. 3, CMake supports usage requirements for libraries. You can specify what your consumers need. Do so. Use interface libraries for logical collections of settings. This is the way CMake is evolving. 4, use imported targets for external requirements, for external dependencies. They should come ideally from a package config file. Give them, they can have usage requirements as well. And 5, be aware of the developer UI workflow, of the potential of the configure loop. So expect configure to run multiple times, and give your project sensible configuration options. And that is all. Thank you. We have a couple of minutes if there are any questions. Yes?
Yeah, you talked about the stuff that is, or I guess you focus on modern CMake. I recently had a discussion with a colleague regarding globbing for source files. What are your thoughts on that?
Looking for source files?
Yeah. Globbing, like instead of if you specify a target.
Oh, globbing, yeah. Yeah, that is something I did not fit in the presentation. There are ways in CMake to glob for files on a disk, and sometimes this is used for gathering the source files of a target. The problem is that when you do that, CMake will not know to rerun itself when the set of files changes. If you do not list your source files explicitly for a target, but if you glob for them and then you add another file, then on your next build, the file will simply not get picked up, because CMake does not run on every build. CMake has finished running and you're doing your build in your native build system. CMake has hooks in there to know to reconfigure if the CMake files change. That is there. If you mess with your CMake list and then hit F7 in Visual Studio for build, then CMake will run first because the CMake list has changed. But so if you add a file manually, it will pick up and it will get included in the target. If you're globbing for them, then you will not get this because CMake will not know. There is now a mechanism to have CMake recheck certain globbing expressions and rerun the configure step if this changes, but I think this slows down. every configure step needlessly, and I don't know whether it is 100% reliable with all generators, to be honest. So I know it is there, but I know CMake developers themselves discourage using this for source files anyway. The preferred CMake, what CMake developers themselves suggest is you list your files explicitly so that you know that when you change them, when you change the list, you add or remove, the build system will get regenerated, will pick up this change. Okay, if there are no more questions, then thank you again.